Okay, so welcome everyone. I'll just say a few words at the beginning. Um, this particular idea of having this seminar was concocted on the island of Cres in Croatia as we had the Koopman Operator Forum there. It's a continuation of the idea that we're a community. We're all working on different problems in a similar initial setting. And so we should somehow have continuous interactions. And I think it's wonderful to see that the group that is assembled here. I see a lot of familiar faces. I see also a number of people that I haven't met before, and I'm enjoying the fact that they're here as well, and would enjoy the opportunity to meet them in person. Um, the purpose here is to get continuously informed about the new developments, new interesting ideas in the context of Koopman operators, applications to machine learning, obviously dynamical systems underpinnings, and that should pertain to theory, computational aspects, and applications. So we're hoping to have speakers that speak to all of the aspects of this activity. We have a great speaker to kick this off with, and so I'll have Cindy introduce and kick it off. And I do want to thank Cindy for um, organizing this. There was a lot of effort going into this, and clearly from the number of people that have logged in, it's already a success. So thank you, Cindy.
Thanks, Igor, and thanks everyone. And thanks, Jason, for taking the time to speak to us. And I'll give you a brief introduction. Jason Bramburger is an assistant professor of mathematics at Concordia University, and previously he was an NSERC postdoc fellow at Brown University and a PIMS postdoc fellow at the University of Victoria, and a member of the Bronson-Coutts research group at the University of Washington. And in 2021, he was named a fellow of the Institute of Advanced Study in Guildford, UK, and his mathematical expertise is in dynamical systems, which he applies broadly to problems in pattern formation, wave propagation, spatial chaos, and data science. And Jason has a passion for outreach and effective communication and has demonstrated by expository articles and active YouTube channel with course lectures on differential equations, mathematical modeling, and dynamical systems. So Jason, take it away.
Wonderful. So before I begin, I want to emphasize thank you very much to Cindy and to Igor and anybody I might have missed working behind the scenes on this. It is a real honor to give this talk, especially because I can see who's in attendance. There's a lot of people who I admire, a lot of people's work that I look up to quite a bit. So I'm not entirely sure if I'm worthy of the first talk here, but hopefully somebody in the audience will find some value in this. So. I'm just going to try and get rid of my panels here so I can make it a little easier. But that means that I also can't see the chat very well. So maybe, Cindy, if I can ask if there's something going on that I'm not aware of, maybe you can jump in.
And do you prefer kind of questions in the middle, or do you prefer at the end?
Yeah, I mean, it doesn't matter to me. I'm happy to, I can answer questions in the
Okay.
middle as well.
So
Yeah.
if I see a chat, and I'll let you know.
Wonderful. Okay. Okay. So thank you all for being here. Like I said, it is a real honor to be giving this first talk. So what I'm going to tell you a little bit about today is my work in polynomial optimization, and in particular, given the nature of this seminar, I'm going to talk about its sort of unification with the Koopman operator. Now, my expectation is that, if you're here, you probably have some familiarity with the Koopman operator, but also you might have much less or maybe no familiarity with polynomial optimization. So I'll try and spend a little bit more time on the polynomial optimization part, and maybe I'll go a little quicker over the Koopman part because I think maybe once you have all the pieces, you can put it together really nicely. So, with that being said, I have like maybe a shameless self-promotion, although I do feel some shame for this. But I wrote a book for SciAm, and in particular, this introduces a lot of ideas around the Koopman operator. Primarily, this is aimed at graduate students, but of course, it could be a nice resource if you're looking to sort of familiarize yourself with maybe something a little bit outside of your discipline. But everything I'm going to talk about today is primarily in chapter 4 here. And there's a full Git repo. You can, it's an example-driven exposition. You can recreate every single example and hopefully maybe adapt them to your own. Okay, so now, when it comes to dynamical systems, maybe if you think back to your undergraduate, maybe your graduate education, the first thing that you really learn to do when you analyze a dynamical system is you typically focus around specific points or trajectories, right? So, day one maybe is identifying things like fixed points or steady states. And then maybe you can step up the complexity a little bit and you can start looking at periodic orbits, or maybe you can start looking at connections between these things or their local stability properties. But effectively, all of this boils down to a fairly microscopic analysis of a dynamical system, right? You're really focusing in on a single trajectory, maybe, local, its dynamics local to it. But really what I want to do is I would like to take a more macroscopic perspective on dynamical systems. And what I really mean by this is looking at sort of global properties of the dynamical system. So this could amount to something like, does there exist an absorbing set or maybe a compact chaotic attractor within the system? Or in particular, if you're thinking about chaotic systems, typically it's less interesting just to look at individual trajectories, but look at time average behavior of quantities of interest, right? So we're thinking about maybe the ergodic theorem or something like that. Or maybe you might be interested in looking at pointwise extremal behavior of these quantities of interest, right? So like what are the maximal swings that your energy can take on over, say, a chaotic attractor? Or what's the minimal dissipation that can be observed in the system, right? And what I'm going to really talk about today is that these macroscopic, these global level problems of a dynamical system can be tackled using what I'm going to call auxiliary functions. Now, before I tell you a little bit about what auxiliary functions are, I just want to emphasize there's another piece of this puzzle, and that is this sort of statistical perspective, right? This is the realm of like proper ergodic theory where you start talking about invariant measures, ergodic measures, physical measures. And it turns out that these statistical properties can be attacked using the same methods that I'm going to introduce for auxiliary functions today. And it turns out that they are a dual formulation to what I'm going to set up. And what I'm going to show is that, or what I can explain to you is that it's dual in the sense of both like a functional analysis duality, but also in the sense of an optimization duality. Okay, so but I'm going to focus on the auxiliary functions today because I think it's a little more tangible. Okay, so I said that I'm going to tell you about auxiliary functions. So the first thing that we should do is we should try and identify what they actually are, right? So there's a whole class of statements about dynamical systems that can be proved using smooth scalar functions whose evolution along trajectories obeys pointwise inequalities, right? So maybe you're as the sort of Koopman fans that you are in the audience here, maybe some alarm bells are already setting off, right? You can see the smooth scalar functions. But what I want to drill down on is this sort of evolution along trajectories. Because effectively this is captured by what we call the Lie derivative. So here I'm going to give it to you in the full Markovian process, stochastic process formulation. If you don't like that, if it's kind of making you seasick, that's okay. We can take it away and just do pointwise evaluations within these scalar functions. But effectively what the Lie derivative captures is it is a directional derivative in the at least expected direction of the flow of this stochastic process or this dynamical system. And there are many places that we can actually calculate out this Lie derivative in closed form. So in ordinary differential equations, this is our familiar maybe f dot grad operation. Or if you're looking at discrete time dynamical systems, this is the sort of discrete gradient operation here where you can see that composition taking place. But if you look at maybe stochastic differential equations, you'll probably be familiar with this as the generator of the stochastic differential equation. And you can formulate this thing for maybe random maps as well. You know, all kinds of Markovian processes. We can show that this thing exists. So the question is, what are some examples of auxiliary functions? Well, the most familiar example, maybe the only example that most people can name, is that of a Lyapunov function. So this is, again, if you took that dynamical systems class in undergrad or in grad school, this is probably the one that you learned. So what you can see here is that a Lyapunov function is defined by these three characteristics. So here, I want you to really pay attention to the fact that, you know, these are pointwise inequalities. They're holding everywhere in space. And in particular, number 2 here involves my Lie derivative. Now, you'll notice that I didn't specify what kind of Lie derivative this is, because if you just swap in the appropriate Lie derivative for any kind of Markovian process, you can get a Lyapunov function. So you can get stochastic Lyapunov functions or whatever it needs to be, discrete time, whatever. That third condition is just guaranteeing your level sets are compact so that you can get actually these stability characterizations. But you can go way further, right? There are all kinds of extensions and variations of the Lyapunov function. So my personal favorite is a LaSalle invariance principle, which basically generalizes this from just asymptotic stability of a fixed point to, you know, finding attractors and things like that. But you can use these Lyapunov-like functions to find forward reachable sets, or some work that I did during one of my postdocs was to identify barriers and trapping boundaries and find invariant regions within these systems. Now, something else that you can do with auxiliary functions that maybe is not as familiar is you can use them to bound long time or infinite time averages of quantities of interest. So the basic idea here is that, you know, you imagine you have some sort of quantity of interest associated to your dynamical system. So, you know, maybe if you're interested in fluids, it's like energy or dissipation. If you're interested in convection, it might be heat transport. You know, if you do a lot of coupled oscillators, it could be the Kuramoto order parameter. But effectively, what you want to do is you want to take the time average of this quantity of interest over a trajectory, right? So it's going to basically depend on where you start here. And you can do this in discrete time if you want as well. But you can ask a larger, more macroscopic problem. You could say, okay, what if I have an ensemble of initial conditions, and I would like to know what the maximal possible time average that can be achieved over all of these initial conditions, right? You could also formulate this as a minimal time average as well if you'd like. But it turns out that this can be turned into an auxiliary function problem as well, okay? So here you get, again, you can see this, my if statement. You see a pointwise inequality. In red there, you can see the Lie derivative showing up. Again, any sort of Markovian process will do the trick here. And in this case, U is a scalar quantity, right? So you're given the freedom to choose the auxiliary function and find the smallest U. And, you know, with a little bit of integration here, you can show that value of U puts an upper bound on all of the possible time average over some forward reachable set or forward invariant set. And you can get a lot more interesting information about this. So for example, if your set that you're doing this over is compact, maybe like the Lorentz attractor, for example, then as an optimization problem, so searching over all possible smooth auxiliary functions, the smallest possible value of U is exactly the maximal possible time average that can be achieved. And you can go even further here because these optimal auxiliary functions that give you, you know, the best upper bound here, they contain information about the trajectories that actually give you that maximal time average. So here I'm on the right here, you can see this is the Lorentz system, you know, the nice butterfly, and you can see this sort of anti-heat signature of the shortest period unstable periodic orbit. So what I mean here is, you know, sort of traced down in blue. And this is the kind of information you can get. In this case, that shortest period unstable periodic orbit maximizes my quantity of interest for this system. And just briefly, there's here you can also do this for bounding pointwise extrema as well. All I really want you to notice is in red again, the Lie derivative shows up. Effectively, this is using a bunch of Gronwall inequalities. So I'm not going to spend a lot of time on this, but I just want you to know you can do it. Okay. Okay, so maybe, hopefully, if you haven't fallen asleep, you have maybe convinced yourself that auxiliary functions might be a useful thing for you to look at. And so now you have this question of how do I actually find them? How do I work with them? Because again, if you think back to your Lyapunov functions that you encountered maybe in grad school or something, the worst advice anyone can give you is try and find a Lyapunov function because there's no real algorithm or prescription for finding them. Well, here what we can do is we can make a simplifying assumption. We're going to assume that the right-hand side of our dynamical system is polynomial. And I can generalize this in 100 different ways if you don't like this, but just bear with me, okay? Well, if the right-hand side is polynomial, maybe what I could do is I could search for polynomial auxiliary functions, right? So I can essentially expand these things in a monomial basis. And the first thing that you can prove is that your Lie derivative is going to be polynomial as well, right? It's basically just a derivative here. So effectively, this reduces the problems associated with auxiliary functions from satisfying pointwise inequalities to basically tuning coefficients of these auxiliary functions to make those inequalities satisfied. And so it feels like things might have gotten easier, right? I mean, I just have to tune a finite number of coefficients. But unfortunately, this is actually an NP hard problem in general, right? So if you have a high dimensional space that you're working on or a high degree polynomial, this is just not going to happen practically. But it turns out that there is a way to make this computationally tractable at least. And that is to replace your inequalities with what are called sum of squares constraints. And what this means is that you are going to literally tune the coefficients, not so that you can get inequalities of these polynomials, but tune them in such a way that you can rewrite that polynomial as a sum of square polynomials. So like x squared plus y to the 4 plus x minus 6y to the 10. And what we know is that, squares individually are non-negative. Sums of them are non-negative. And so we get our inequality constraints sort of for free or as a consequence of this tuning.
Is it obvious that we're not missing, like, what if it's sum of squares, but it's not polynomial squares?
I'm sorry. What was the question?
Sorry, okay. I understand the sum of squares, but do they have to be polynomial squares? By assuming polynomial squares, are we maybe missing some possibilities?
Oh, well, so there are a few different things that you can do here, right? So my assumption says that, assume things are polynomial. There are many, many ways of generalizing this to rational functions, trigonometric functions, all kinds of fun things that you can do. And then effectively you're still looking at squares, but you're just looking at squares of trigonometric functions or whatever it happens to be. Furthermore, there's all kinds of proofs that tell us that using things like Weierstrass approximation theorem, that we can really sort of restrict ourselves to polynomials and we can get good approximations of these non-negativity constraints. Actually, this falls back onto results from algebraic geometry, which are called I'm going to mispronounce this. I apologize to the Germans that are in the room. Positivlandssatz or something along those lines. Again, I'm very sorry. But there are many reasons that we can actually work with these polynomials.
Okay, thanks.
Okay. So the other nice piece of this is that by searching for sum of squares representations, we can actually translate these things into semi-definite programs. And the nice thing about semi-definite programs is there's been, decades of work creating interior point solvers that allow us to sort of solve these things computationally. So let me just show you a really simple example, okay? Here's my planar ordinary differential equation. If you plot the vector field or the phase plane, you can see this little plot on the left-hand side. It looks like everybody's falling into zero, and so maybe you might conjecture that there's a Lyapunov function associated to this thing. Well, the way that you would set this up using sum of squares programming is you would say, try to build me a Lyapunov function that satisfies these constraints. Now, is SOS means tune the coefficients in such a way that this can be rewritten as a sum of squares. And what you can see is that I have these 0.001 x squared plus y squared. These are to enforce strict inequalities away from zero. So again, these are computational. So we want to get strict inequalities to get asymptotic stability. But effectively, what you can see is that all three of those conditions for the Lyapunov function are built into these. In fact, the coercivity conditions are coming from the 0.001 piece. And so, tucking some computation behind the curtain here, you could look for a quadratic Lyapunov function, and the output of that semi-definite program would be these coefficients here given to you by about 4 decimal places. So you get, at least a numerical candidate for a Lyapunov function that satisfies these sum of squares conditions. And so just, this is your very quick introduction to all things polynomial optimization, which is, one of my obsessions in mathematics, especially for dynamical systems analysis. But what I want to really emphasize to you is that, through these sum of squares conditions, we can turn these things into semi-definite programs, and we can make these computationally tractable. We can tune these coefficients. We can find these auxiliary functions. And the other piece of this is that, as I mentioned at the very beginning of the talk, there's, you can set these things up on the measure side as well. So there's lots of people who have done some great work around this. And effectively what happens here now is that you no longer have non-negativity of polynomials, but you have non-negativity of measures, which again, you can play some nice games. You could turn these into semi-definite programs, and life is good. And so this leads me to the bigger question, and this sort of gets us into the theme of this lecture, or into the theme of this seminar series, is what happens if we don't know the dynamics? Because if you think about everything that I've done so far, I'm assuming that I know at least the Lie derivative in order to build these auxiliary functions, right? So you could ask this question, what if you just give me a little bit of data from a system, and could I use auxiliary functions to maybe prove that system is globally stable, right? It has a Lyapunov function. Or could I bound time averages, right? So if you have really expensive to create data, like fluid data or something like that, can I bound some time averages so you don't have to run expensive simulations for a very, very, very long time? And then on top of this, there's a whole other control aspect of this that I'm not going to get into, but I do know that there's a lot of people in the audience that are interested in control, and we can build these into finding control Lyapunov functions as well, that I would be happy to speak about offline. Okay, so this is where Koopman really comes in, okay? And I suspect that the keen eye of most of the people in the audience have already sort of identified where Koopman is within this formulation. But, if you'll allow me to just explain for a second here, maybe you take a break and grab some water or something. But in our case, I'm going to, like I did earlier, I'm going to use the stochastic formulation of the Koopman operator. Here, we're going to talk about, the expectation forward in time of this Koopman operator semi-group. But again, if you don't like this stochastic formulation, of course, you can always just use pointwise evaluations. That's perfectly fine. But the most important piece of this is that as a one parameter semi-group, the Koopman operator has a generator. And as I suspect many people in this room already knew, the generator of this thing is exactly that Lie derivative that I've been harping on about throughout the talk here, right? And so if you'll sort of follow my chain of reasoning for a second here, we can think back to, the past, 10, 15 years of excellent work by many people who are in this audience right now, that have pioneered methods that allow us to approximate at least the action of the Koopman operator on finite spans of functions from just data. So follow me with my chain of reasoning. If you give me the data, I can approximate the Koopman operator. If I can approximate Koopman, I can approximate the Lie derivative. if I can approximate the Lie derivative, I now have access to auxiliary function methods by just sort of swapping in the data-driven Lie derivative with the exact one that should have been there. But that means now that if I have access to these auxiliary function methods, I have access to saying something about the global behavior of the dynamical system that underlies or that generates this, this data that you might have given me. And in particular, when we implemented this method, as I should mention that this is that this was done in collaboration with my friend and colleague Giovanni Fantuzzi, we appealed to extended dynamic mode decomposition. So effectively, a sort of Galerkin approximation of the Koopman operator. And I do want to sort of talk about this for a second because the implementation might be slightly different than what you're used to here. And that's because we're trying to achieve something slightly different than what one might be used to with extended dynamic mode decomposition. So in our case, we're going to assume that we're given data points. In this case, we're going to assume that these are ordered pairs in the sense of what's happening now and what's happening next. They don't all have to come from the same trajectory. They could be IID samples or whatever it happens to be. But as long as you give me them in pairs, I'm happy. And then what I'm going to do is I'm going to define two bases or two spans of functions, which I'm going to call the expansion dictionary and the image dictionary. Okay, so this is maybe the slight nuance or the slight difference to what you might be used to. But effectively, what we're going to do here is we are going to approximate the action of the Koopman operator on the expansion dictionary in terms of the image dictionary. Okay, so this is why we're gonna use two different dictionaries here. We want to sort of capture that overflowing property. We're not looking for eigenvectors and eigenvalues. So this is why we can allow ourselves to use two different dictionaries. And the names of these dictionaries correspond to what they're actually doing with these auxiliary functions, because this expansion dictionary becomes the dictionary of functions or the basis of functions you're going to expand these auxiliary functions in. So typically, you know, the way that I would envision implementing this is with polynomials, right? So the expansion dictionary might be up to some degree. The image dictionary might be up to another likely higher degree for the polynomials. And effectively, in this case, we're going to approximate the Lie derivative just with a discrete gradient operation. And again, just like the Koopman operator, the Lie derivative is now giving you the approximation of the Lie derivative on the expansion dictionary in terms of the image dictionary. Okay. So before I talk about any theoretical results or anything, let me just give you a nice application. Okay, just a fun, really simple application, just so you can see, I mean, what this could actually do. Okay, so here I'm going to take data from the Vanderpool oscillator, just a simple nonlinear oscillator here. You can see the streaming data happening in the top left corner here. And what we might be interested in is maybe the system energy, okay? So sort of loosely defined just as this square of each component added together. And you might want to ask yourself, you know, what is the maximal achievable system energy or time average system energy of this system over, you know, all possible initial conditions in this dynamical system, okay? Well, what you can see on the bottom left here is you could just average the system energy, right? I mean, everything converges to the periodic orbit. There's only two limit set or two components of the limit set. There's the periodic orbit and the unstable origin. The origin gives you time average 0 for your energy. So the limit cycle is going to maximize the time average here, right? So of course you could just average the data as it comes in. And this is what this running average in the bottom left corner is. Now, because I purposely chose my data to start very far away from its eventual fate on the periodic orbit, you can see that this running average is taking a long time to converge, right? It's got to eliminate out some transients here. And so you can see that it's finally starting to level off. But this requires a ton of data. So let me just show you, here's an overwhelming table of numbers that I don't want you to stare at too much, but there are a few pieces that I want you to draw your attention to. In the very first column, I have what time you are integrating up to. Okay, so you can see on the bottom left, I've integrated up to about 380 or so. That very first row is integrating up to about time 100. And then in the very last row, what I've called the SOS row, this is using the exact Lie derivative. This is the best possible upper bound you could come up with if you knew the system dynamics and employed all of the auxiliary function framework I just showed. In particular, the highlighted orange value is the sharp, at least to 4 decimal places, time average along that periodic orbit. Again, you can do this by just running the data for a very long time. Now, take a look at that first row, that 100 up time integrated up to 100, and the deg v columns indicate the degree of my expansion dictionary. So skip all the way over to degree 10, right? I got to choose this, so I can just pick the degree high. Take a look at that. Using only integration up to 100, I can get a bound on the maximal possible time averaged output here that is 0.01 away from the exact value, right? And in particular, if you look at the empirical average up to time 100, I'm just over halfway there. So this provides a lot of optimism for us, right? It tells us that we should be able to get good bounds on these things using way less data than you would need to actually just average these things. And of course, this has massive consequences for places where data is difficult or expensive to generate. Okay, so then of course, there's a fairly rigorous theory that has been developed. I can't take much credit here because it's been developed by many people before me, that really tells you why we should expect such good performance here, right? And this comes in the form of convergence results in terms of how the data is sampled and for these Lie derivatives, right? So we can make some assumptions. You're sort of sampling data with respect to some distribution, and then the sampled averages of your data converge in the infinite data limit to these mu expectations, right? So these are standard assumptions to get your Koopman operator to converge here as data goes to infinity. And this can be satisfied in two really simple ways. You can take IID realizations from this distribution, a little bit harder to do in practice, but it provides some really nice convergence results. Or as you saw with the previous case for the van der Pol oscillator, you can take ergodic trajectories, right? So sort of just letting one single trajectory run and wind up on the attractor. And effectively, what we can prove here, and like I said, we're not the only ones to prove this. The only thing that we did is use different size dictionaries and just did it in the fully general Markovian setting. As you can see in the top right corner, there's a lot of other references that we built upon. But effectively, we can see that we have this almost sure convergence here. So you can see that there's 3 limits. N is the amount of data. M is the size of the dictionary, the expansion dictionary you're using. And tau is the time step because we're talking about a Lie derivative here. And we can also show that those 2 outer limits, the time step and the M limit, those can be exchanged, but the data limit that's hidden inside there cannot. And like I said, there's a few pieces that we extended, but theirs are fairly minor. They are not our major contributions to this. But the one thing that I would like to emphasize is we also explored the link between extended dynamic mode decomposition and a similar related method called generator extended dynamic mode decomposition. And we were able to show that their approximations from data for EDMD and GEDMD might not coincide. In fact, GEDMD might not converge at all. So we identified some potential problems with using GEDMD as opposed to maybe more standard EDMD. Okay. Then this, as a slight foray before I show you some more maybe fun examples for dynamical systems. I had a master's student here, Daniel Fasler, who did some really cool work with a collaborator of mine, Simone Brugia-Paia, professor in my department as well. And Simone comes from the background of just straight approximation theory. He doesn't do any dynamical systems, but he does a lot of these sort of least squares problems, deep learning problems. And one thing, that you can prove, in people have proved this a few times, and it really just comes from like Monte Carlo theory, is that if you take IID samples of your data and you use an orthonormal dictionary, then basically the convergence rate of these Lie derivatives in the amount of data here converges like 1 over the square root of data, right? So again, this is not an interesting theorem. This is really just Monte Carlo convergence, right? And so what Daniel was kind of playing around with was, well, does it matter what kind of samples you're choosing, depending on the measure versus the dictionary? And as you can see from this picture here, you see all this like uniform the uniform measure with Legendre polynomials, the Chebyshev measure with Legendre polynomials. He was kind of mixing and matching, and we found that there was no real way of sort of speeding this up or getting around this. In fact, there was actually no real way of slowing it down either, other than a prefactor. But what Daniel really did, and this is something I think that maybe this audience will find interesting, is Daniel actually sort of unified and applied some really nice results that show that you can actually look at a sort of double limit here, right? So this is a double limit in terms of the amount of data and the size of the image dictionary. And it turns out that if you grow these things together, so as data is coming in, you're sort of enlarging the expansion dictionary, you can get super polynomial convergence of these data-driven approximations. Of course, this would work for the Koopman operator as well, but here I'm just writing it in terms of the Lie derivative. But I'm just showing you, one example. This is Daniel's thesis is full of this stuff, and we're in the process of putting this together as a nice paper. But here we just took data, IID data from the logistic map, and you can see this very quick exponential convergence where you are growing the size of the dictionary in a sort of, you can see this sort of m log m, m squared log m. So it's a very precise way of growing the dictionary in order to grow with the amount of data that comes in to get these incredibly fast exponential conversions. I mean, take a look here. I mean, the size of these dictionaries are plotted along the horizontal axis. We're talking, they're not very big, right? We're talking machine precision by about a basis of size 30, at least for this example. So now let's turn back to some actual applications of this. And so that's what I would like to do for the last maybe 10 or so, maybe 15 minutes of my talk, is just show you two big examples that I'm quite proud of that I think hold the key for a lot of the future applications of this stuff. So the example that I would like to start with is the Rosler system. Now, I know that, as dynamical systems people, we're supposed to do everything with Lorenz, and I've already shown you pictures of Lorenz. But if people give more respect to the Rosler system by the time I die, I will die a very happy man. I love the Rosler system. I think it is my favorite simple chaotic system. And let me tell you why I love this system, and maybe you'll come to love it as well. Okay, so nice, simple 3D quadratic dynamical system, just like Lorenz, but it has this incredible property that if you put a Poincare section at, in this case, x1 equal to 0, okay, then numerically, x3 almost goes through 0. Now, of course, it cannot go through 0 exactly, and that's because the dimension of the attractor is larger than 2, right? It's a fractal dimension. But numerically, this means that you can kind of disregard those x3 values, and you can just track the x2 values every single time you pierce this Poincare section. And in particular, if you plot out the data with the vertical axis being where you're going to go next versus where you are on the horizontal, you effectively see that the governing Poincare map here is, this single hump function. It looks like all of these functions that you would learn in chaos theory, right? It looks like it's amenable to renormalization theory or obeys Feigenbaum's results as well. And here's what I'm going to do. I'm going to use that as data to seed my method. Now, it's important to note that this is, in some sense, a truly data-driven application in the sense that I do not know the mapping, the explicit form of the mapping that governs this. You can try and fit a quadratic model to this thing, but if you look close enough, you can see this thing is not quadratic. Those arms are just a little too straight. And so I'm going to use this data to seed a method. And here's what we're going to do with it, okay? I'm going to come up with 1,000 randomly chosen functions that I want to bound the time averages of. And these functions are just going to be generated by taking my expansion dictionary and creating a random vector of coefficients and generating a function in that expansion dictionary, okay? They have no physical meaning. But what I'm going to do is I'm going to increase the polynomial degrees in such a way that I should get very sharp bounds on the infinite time averages of these things. Now, if you go all the way back through my talk to maybe the third or fourth slide where I introduced to you this time average stuff, I said that those optimal auxiliary functions, they contain information about which trajectories will maximize these time averages. And in the case of this discrete Poincare map data, these time averages are going to be maximized on the unstable cyclic points that sit within this thing, right? So the periodic points of the Poincare map. So that means that I could potentially extract these periodic points from the Poincare map. And what we know is that, these periodic points approximately tell us where the unstable periodic orbits of the Rosler system pierce this Poincare section. So I could use a shooting method and I can extract unstable periodic orbits from Rosler. And here's what we're going to do. So what I did is I simulated up Rosler. I collected 810 data points from the Poincare map. I mean, it's worth pointing out here that that's not a whole lot of data relative to what I could have generated. And my expansion dictionary is going to be Chebyshev polynomials up to degree 20. And my image dictionary will be Chebyshev polynomials up to degree 80. So really just cranking up degrees here in order to get good results. I'm not interested in what happens as I increase these things. I just want the results at this point. And here's what I can show you, right? So what we find is that, hidden within these 1,000 random observables or quantities of interest that we bounded the time average of, is a whole bunch of locations of unstable periodic orbits that are within this Rosler system. So here what I'm showing you is that the method is able to find all of the low order unstable periodic orbits for the Rosler system. And the way we can check this is just by looking at the data as well. So that's what's plotted in each of these panels. And then you can also see the corresponding continuous time periodic orbit in that Rosler system next to these things. But of course, you are sitting at home and you're not impressed, which you shouldn't be, right? Finding short period periodic orbits in the Rosler system is something we could have done in the 80s, probably, right? Like this is not a particularly impressive application. It just shows that this can be done. What I think is particularly interesting about this is that the method shows no preferential treatment to short or long period periodic orbits. In particular, we're able to pull out really long periodic orbits as well. So here I'm just giving you some examples. Here you can see a period 13 and a period 17 periodic orbit. I'm referring to their periods as how many times they pierce the Poincare section before coming back on themselves. I believe we have like a period 19 as well, but the nice thing is here, it doesn't just find those short period pieces. It also shows no preferential treatment to short or long, and we're able to pull out these long ones as well. Just let me grab some water here. Okay. So as another demonstration of what I think is the sort of forward-looking utility of a lot of this work is an application to fluid flow. Okay, so here's what I'm going to do. I'm going to look at the shear flow model, very sort of standard model. You have a three-dimensional fluid velocity. This fluid is bounded between two sheets that are being pulled in opposite directions. They're shearing. And what we know about this system is that the laminar state is always locally asymptotically stable over all Reynolds numbers. Okay. What we also know about this system is that for very low Reynolds number, that laminar flow is globally stable, but for high Reynolds number, there is a chaotic saddle or a turbulent saddle in which you will, if you mix up this fluid or if you initialize it away from the laminar state, you will see an unsustained turbulence taking place before this thing settles into the laminar flow again. And that means that there are, in the presence of these chaotic saddles, there are other states in the system. So you cannot have global stability of the laminar flow state, right? You can have unstable periodic orbits or unstable relative periodic orbits as well in here. And so what we would like to do is I would like to identify the Reynolds number, or at least bounded from below, where this transition takes place, where you lose global stability of this laminar flow, where this phase transition happens. So let me show you how we're going to do this. And I'm going to show you so we have better results on actual fluid data now, but they're not ready enough to be sort of presented to a wide audience yet. So I'm going to show you a sort of simple demonstration where what we did is we didn't actually work with the full shear flow model. What we did is we used the Moelis et al., the 9-mode projection of this model. So the same way that Lorenz got his famous ODE from a convection model, Moelis is able to come up with this 9-dimensional ODE from the shear flow model. Okay, and so then what I'm going to do is I'm going to take 9-dimensional time series data at different Reynolds numbers. So over a range of Reynolds numbers, just from random initial conditions in this 9-dimensional model. But again, I mean, 9 dimensions still, it's if you're thinking polynomials here, thinking about quadratic polynomials in 9 dimensions, that's a lot of information. That's a lot of variables. And so what I'm going to do is I'm going to do a little bit of a random feature method. I'm going to create 3 random orthogonal vectors and 9-dimensional vectors, and I'm going to take that 9-dimensional data from the Moelis model, and I'm going to project it onto each one of those 3D or those 3 orthogonal vectors. And then what I'm going to do is I'm going to try and find good upper bounds on the time average of this, what I'll call the energy in this projected random orthogonal mode model, right? So just taking the sum of each component squared. Now, the data is set up in such a way that the laminar state gives a time average of 0. In fact, it has 0 energy. And so if I get an upper bound that converges down to 0, it tells me there's nothing else in the system but the laminar state. However, if that upper bound starts getting stuck somewhere, it tells us that there should be something else in this system. So let me show you some pictures. Here's what I've got. Along the horizontal axis, I'm sweeping over Reynolds numbers from 10 to 100. Along the vertical axis, I'm plotting the upper bound, and each one of these colored curves is for a different size of the expansion dictionary. Again, this is my degree V that you saw earlier with the van der Pol model. So take a look at the blue curve for a second, okay? So the curves are very not pretty, but that's because in some sense, this is, again, real data. It's incomplete data, of course, right? Because I'm just simulating it up. But take a look at this. The blue curve gives basically an upper bound of 0 from about Reynolds number 10 to 20. It tells us basically there's nothing else in that system but the laminar flow up to about Reynolds number 20. Then you increase the degree of the expansion dictionary, And you can say there's nothing in the system up to about Reynolds number 30 and about 45. And then when you get to degrees 11 and 13, take a look at those pictures, the purple and the yellow curve. Both of them are sort of jumping at almost the same spot, right around Reynolds number 80. Now, this is very interesting to us because what we know about this Moelis model is that the smallest Reynolds number that anyone has detected a non-trivial, so non-laminar state is 80.5. And at 80.5, there is a saddle node bifurcation in which two unstable periodic orbits are birthed. So effectively, that 80.5 functions as an upper bound, while our results right here function as a lower bound, and we're getting very good accuracy here, telling us somewhere, very close to Reynolds number 80 that you're seeing this phase transition happen. And I can tell you that for the full fluid model, we're seeing something very similar as well. Okay, so I think I've taken enough of your time today. I would like to thank you all for watching, and I just want to give you a brief summary, right? So the important aspect of this is that it sort of unifies a lot of what we already know about the Koopman operator, and in particular the Lie derivative, with another one of my sort of loves in dynamical systems, and that is polynomial optimization. And what this allows you to do is get global information about the dynamical system without doing system identification, right? There's no like Cindy step in the middle here. It just goes straight from data to information. And of course, there's all kinds of rigorous analytical justification for why these things work. I briefly commented on some, but many people in this audience have also done those things. The one thing that I really love about this is that the method is completely agnostic to deterministic or stochastic data, right? You just give me the data and it will, we can show that it'll converge to the appropriate Lie derivative, and you don't have to do any pre-processing, especially at the polynomial optimization stage. And then the last piece of this, I teased the invariant measures piece. I said that they come as a dual version of this. So as an optimization problem, you're going from continuous functions to the dual space, which is your space of measures. But then also on the functional analytic side of this, you're going from the Koopman operator to its dual, the Perot and Frobenius operator. And so everything that I did today can be done on the side of invariant measures as well, if that's the side that you'd prefer to come at this from. Okay, thank you all for your attention. And most of this work is coming from these three papers right here. I can maybe exit out.
Thanks, Jason, for that wonderful talk. Now we open up for questions or comments.
Well, if it seems everybody's quiet, so I'll start. So wonderful talk, thank you.
Thank you.
So it's interesting because it brings me back to some good old times, and I don't know if you know this, but the first time that Koopman operator methodologies have been used in data-driven context was in about 1992. I don't know if anybody on the call knew this, and it was used in the context of taking time averages and identifying invariant sets by them. Yeah,
Okay.
I proved the ergodic partition theorem in my thesis, and that appeared in 94, but it was done around 1992. But I have some questions around that. First of all, there is a really nice work of Jenkinson on ergodic optimization. I don't know if you know that one.
I'm not familiar with the exact paper, but maybe some of the results. I'm not sure.
Yeah, I can send you some.
Please do.
It's a worthy set of references in ergodic theory, some 10, 15 years ago, I think. But the other question that I had is, if you look at something like Wanderpol or any limit cycle or toroidal attractor, the convergence you get from naive time averaging, just time averaging, forget approximations with libraries, is
Mhm.
1 over n.
Yeah.
That's provable. Um, you can actually do better. So Jim York and Sudho Das have done a sequence of papers. I think Dimitri is still here, might be still here. Sudho worked with him later on. And they proved exponential convergence. You also get exponential convergence from the cycling methods, the approximations using unstable periodic orbits. So it would be interesting to compare with some of those because you seem to be getting with the judicial selection of data, you seem to be getting exponential convergence. But those kinds of rates have been produced before. So it's kind of an interesting thing to compare. And I think at the end of the day, you want to contrast how effective this is, how robust it is, how robust these methods are. So anyhow, those are some comments. I don't know if you had a response or.
Yeah, Igor, let me tell you, I have great news for you. Myself and Matthew Kohlberg just finished a paper that should be on the archive by the end of the week about building in these weighted averages to these data-driven methods,
Okay.
and getting this exponential conversion. So I'm very happy that you brought that up because this is very true. Now, for for the record, this also comes at a massive caveat that you only get exponential conversions for limit cycle or quasi-periodic dynamics. For chaotic
Yeah,
dynamics, it does not speed you up at all.
yeah, yeah, that's correct.
Yeah,
But that's well known.
yeah,
That's not news.
yeah, exactly. But yeah, so I think with the Vanderpool example, I mean, I wouldn't read into it too much. We just wanted to see, what could be done here, and gauge performance on like a very simple system. So I mean the point is taken, and then I completely agree, but I wouldn't read too much into that example beyond the sort of
So for
metric.
clarification on Ressler's attractor,
Yep.
you're not claiming exponential convergence, or are you?
No, absolutely not. No, no, no.
Yeah.
So actually to go back to
So
these.
let me point this out. So if you use the cycle expansion methods,
Mhm.
even for chaotic attractors, you can actually get exponential convergence. So the race for doing this using libraries and from data is actually on. If you read Predrag Cvitanovic's book, you'll
Yep. Yeah, of
on
course. Yep.
chaos, you will find it there. So you can get exponential rates of convergence of averages, which is actually quite interesting because that beats the common perception, but it's the consequence that you have an countably infinite number of periodic orbits, unstable periodic orbits embedded in the chaotic sea, and you just sum over them, and the contributions decay exponentially. So it's intuitively actually,
Mhm.
not 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 too difficult to understand, I'd say.
Mhm. No, I mean, Dr. Stefanovic does fantastic work, and that book is wonderful. It's a great resource.
That's all I had. Thank you.
Thank you.
I have a question about this slide. So how did you apply Chebyshev polynomials to, because here you have like a vector of states.
No, sorry, it's only one-dimensional data, right? Because it's, as I said, you're only collecting the x2 state every single time you go through the Poincare section because x1 is equal to 0, so that defines your Poincare section. And I said numerically, x3 is almost 0. I know that it's not 0. It can't be 0, right? It's not a one-dimensional Poincare section, but it is approximately enough that all I need to do is collect the x2 state. So it's really one-dimensional data in this case.
Okay, now that then it's fine. Thanks. Very nice talk. And
Thank
just
you very much.
minor observation for the van der Pol, I thought you took the coefficient 0.1,
Yeah.
but if you want to study like the challenging behavior of van der Pol, it should be bigger than 1, I think.
Yeah, of course. Yeah. As I said, it was just a simple example. Basically, we just wanted to see if you start really far from the limit set, can you still get information here? But I agree.
Thank you.
Yeah.
Yeah.
But I can
Are there any more further questions from the audience?
I have just one little remark because this has been again, thank you, Jason, thank you, Cindy. This has been a wonderful success in my view. We had like 32 people in this talk, and I expect it's only going to grow after this. If people want to see I think it would be nice to organize the after seminar correspondence as well, so we can exchange papers and do things of that sort. For example, I'm happy to send around some papers that I mentioned. If you want to get on the list, send the email to Cindy, and we'll incorporate, make a a little mailing list. Is that okay with you, Cindy?
Yes, that's actually there is
You
one
can
already.
deputize. It's not a.
So something else that Irv and I are talking about is to do like maybe quarterly newsletter of new papers, conferences, whatever is related to the Koopman operator theory. That way we kind of keep each other informed of what's the latest development. So I will circulate around a form for all of you to fill out, and then I'll compile into a nice newsletter, and we can probably post on LinkedIn or social media, and that way we have a continual way to inform each other of what some of the newest work is as well, in addition to just the Zoom seminars. So I'm going to share my email in here in the chat. So if you or your collaborators or students, postdoc, anyone want to be added to the list I'm starting to organize, send me an email and I'll be happy to add you to our list. And the way that we're running this, there are kind of two sessions because this is an international group. We are doing kind of a US, Europe-based time zone this round, and next time will be more of the Europe/Asia and some of those time zones, just so that we can kind of get a spread of people attending and speaking as well. So, and I know that the next one will be in the European time zone, and it might not be very friendly for the US folks, but we do always record and post it on the KOT YouTube, and I'll post a link to, and thank you, Irvin, for helping. He's my co-organizer. He's going to be the European lead when it's the European time zone. To do this, and we'll always send email to keep you informed on the recordings and everything else. Okay. All right. Thanks everyone. We have another one scheduled in December, so I will follow up with more details with that. And that one will be in the European time zone, but the recording will always be available. So, okay. Okay.
Good.
Have a great Thanksgiving if you're in the US next week. And if not, and we'll see you in December.
See you later.
Great. Thanks,
Everyone.
Jason, for a great talk.
Thank you
Goodbye.
very
Thank you
much.
all for coming, and thanks to Cindy and Igor for organizing. Great job.
Thank you.
Thank you.
Thanks, everyone.
Thank you. Goodbye.